Welcome to Lecture 3 of Thermodynamics and Equilibrium, and I'm going to introduce chemical equilibria to you in this lecture. So in the last lecture, just to remind you, I introduced Gibbs free energy to you, and we talked about this equation here that defines the change in Gibbs free energy in terms of enthalpy, the change in enthalpy, and entropy term, which is temperature times the change in entropy. When a process is spontaneous, then the change in Gibbs free energy is negative. This shows that a spontaneous process also depends on temperature, and as we know, disorder of a material changes with temperature. And it also depends on whether the system is endothermic or exothermic, so whether enthalpy is positive, negative, and whether the process leads to a increase in disorder, which would be an increase in entropy, or the simplest way of thinking about entropy. The objectives of this lecture is to introduce equilibria to you, and by doing that, then some terms such as the quotient and the equilibrium constant will be explained. And we're going to also look at the relationship between the changing Gibbs free energy, so delta G, and the equilibrium constant, and equilibria, and introduce Le Chatelier's principle to you, and also the Van't Hoff equation. If our reaction doesn't go to completion, then it is an equilibrium reaction, and we depict this with a two-way arrow showing that the reaction can go in both directions. Note that at equilibrium we don't have a static system. It doesn't stop. The reaction doesn't completely stop. It is simply the point when the rate of the forward reaction, so going from reactants to products, equals the rate of the backward reaction, so going from products to reactants. And so there's no net change in the concentration of reactants and products at equilibrium. We will consider the reaction in terms of Gibbs energy. A bit like our discussion in the previous lecture showing how ice melts, and that the forward reaction is only spontaneous when the temperature is high enough to tip the system so that delta H is less than minus T delta S. You might remember talking about that in the previous lecture. The enthalpy term is smaller than the entropy term in that case, and so delta G of melting is negative. So delta G is important when considering an equilibrium process, and we'll see more about how we can talk about delta G in terms of these reactions as we go forward. We're going to be using this graph quite a bit in the next few slides. So in this graph we have energy, Gibbs free energy, so the total amount of energy in the system, against the extent of the reaction, 0 being the point where we have 100% reactants, and 1 being where the proportion of products is 100%. So you can see that for an equilibrium reaction, the lowest point at the curve will not be at the point where we have products formed. It will be somewhere between where products and reactants are. So it'll show that there is a proportion of both reactants and products at that lowest energy point. And that would be the equilibrium point. For the forward reaction, the standard change in Gibbs free energy for this reaction is minus 32.9. So this is the reaction we're going to focus on, formation of ammonia. And this means that it is an exothermic reaction going from reactants to products, and that the reactants have a higher total energy compared to the products. So you can see that the line at the 0 point on our progress of reaction graph here will be higher than when it gets to the end where we have 100% products, where the line is lower because the overall change in Gibbs energy for the overall reaction is a negative number. And if we think about how Gibbs energy changes during that forward reaction in the formation of ammonia, we see that we get a decrease in G as we go towards that minima point, and then we see that G, the Gibbs energy, increases. And a point of equilibrium, we have our minimum point, and so the change in Gibbs free energy at that point of minimum is 0. At any point on this graph, we can see that the gradient will tell us whether we expect the reaction to be going more in the forward direction or more in the backwards direction to get to that minimum point. The direction of change depends on the ratio of concentration of reactants and products. The quotient defines that ratio at any point along the progress of the reaction path. For the reaction forming ammonia, the quotient is given here. The quotient is the concentration of products raised to the power of stoichiometry of the reaction. So 2 molecules of ammonia form in this reaction, and the concentration is squared. The product is divided by the concentration of reactants, again raised to the power coming from the stoichiometry of the reaction. And this quotient can then be used to help us determine the dominant direction of reaction at any point along our progress of reaction curve. I'm going to show you that in this slide. So, how does delta G change? As we said before, the reaction equilibrium, there will be a minimum point on our free energy graph where the change in Gibbs energy is 0, and that was our equilibrium point. But our quotient can be measured at any point along that graph where we might want to determine whether the reaction is favoured going towards reactants or towards products. With the quotient, we have a way of determining how delta G changes at any of these points along that progress of reaction graph. G changes, as we know, to a minimum, which is somewhere between reactants and products. And the change of G will be negative before the minimum point and positive afterwards. So we can use this equation here, which tells us how G will change going along that curve, and link it to the standard conditions change in Gibbs free energy, which is the Gibbs free energy for the total reaction going from reactants to products, adding to that a component which will tell us where we are on that curve because it's linked to the quotient. And then we will be able to see whether delta G is negative or positive, and therefore the direction of travel for the reaction at that point. We know that the standard change in Gibbs energy to form products is negative for this reaction. And the delta G at any point along the reaction can be calculated if we can determine the quotient at that point using this equation. So we can work out where we are along the reaction. The reaction will go towards products when some of the two components, the standard Gibbs energy change and the term with the quotient, are negative. At equilibrium, the change in Gibbs energy is 0. And if we are at a point further along the progressive reaction, the equilibrium, then delta G will become positive in the forward direction, meaning that the reaction doesn't anymore favour going from reactants to products, and now favours going from products to reactants. Do remember, though, that at any point we do not lead to a static situation. We are looking at two reactions, one going from reactant to product and one going from product to reactant. Equilibrium is not static. You can think of it as a position of calm, like the amount of work you're being asked to do. If the amount of work you are being asked to do is comfortably equal to the rate that you can get the work done, it's not a static state, it's a dynamic state, but it is calm because your in tray is building up as fast as your out tray is building up. Okay, so you don't get overwhelmed and you're at a system of equilibrium. But you're not doing nothing. And that's the same for these reactions. If you see here, these two graphs show that. So you can see here rate of the reactions against time, the rate of the forward reaction. If you start with 100% reactants, initially the rate of the forward reaction will be greater than the rate of the reverse reaction because you will have more reactants than products. But at some point, the rate of both the forward and the reverse reactions will equal, and that is where you have equilibrium. So if you see that as the amount of reactants and products that's formed, you get to a point where there are reactants present and products present, but the total amount of both is not changing. At equilibrium, the quotient is given a different letter. It's given the letter K. Okay. And it becomes the equilibrium constant. And at equilibrium, the change in G, in our Gibbs energy, is also 0. So this means our quotient equation changes and simplifies. Because delta G is now 0, so 0 equals our standard Gibbs free energy change for the total reaction, plus RT, and now we have log of K rather than natural log of Q. So ln is natural log, and I often just shorthand say log. So natural log of K. So you can rearrange that to get a really important equation that links the change in Gibbs free energy for our reaction to the equilibrium constant. Minus RT, R is the gas constant, times temperature, times the natural log of K, the equilibrium constant. So that's our first really important equation link to equilibrium. So in summary, K is the quotient at equilibrium. And if you calculate Q for a particular point on reaction and Q is less than K, then the reaction will proceed in the direction of products. And if Q, your quotient, is greater than K, then the reaction would proceed in the direction of the reactants. Okay, so that's how you can link your quotient, which will change depending where you are in the reaction, to your equilibrium constant, which is a constant because it's only the concentrations of reactants and products at the point of equilibrium. So you would measure the equilibrium constant at the point of equilibrium as the concentration of products, over the concentration of reactants, allowing for the stoichiometry of the reaction, as I showed you before. So this is 16 minutes into a presentation that is approximately 30 minutes long, which is a little long for a screencast. So you might like to take a break here, walk around for a few moments before you sit down and watch the rest of the presentation. So I would pause the presentation here and have a short break. What I'd like us to do now is to think about how experimental conditions can change things. So consider the use of baking soda in baking. This reaction is an equilibrium reaction, releasing carbon dioxide and water. However, at room temperature, the equilibrium constant is 10 to the minus 7. You'll see that 4.9 times 10 to the minus 7. So it's very, very small. In fact, it is so small that if you think of products over reactants, we are dominating as reactants. It's a very small number over a very large number. So you could say that this reaction has not occurred at all. Okay. And you'll notice that at room temperature, delta G for the reaction is plus 36. So also saying the reaction doesn't occur. So you need higher temperatures for this reaction to occur and for this equilibrium to shift to a point where products are forming. At higher temperatures, we then see that the equilibrium constant shifts to 55. So now there's more product than reactant at equilibrium. There's still a component of both. That number isn't ridiculously high to say there is no reactance. And you'll notice that the Gibbs free energy for the reaction is now a negative number. So you can see that the equilibrium constant changes with temperature. It is not constant at different temperatures. It's only constant at a single temperature. And you can also see that baking soda doesn't work unless you have it in an oven or in a system where it's warm enough for the reaction to occur. If you want to maximize the product, then you need to think about how different variables shift this equilibrium position. And that is Le Chatelier's principle. So let's talk about that on the next slide. First of all, let's not focus on temperature, which is a little bit more complicated. Here we have a reaction, and we're going back to a formation of ammonia reaction again. Nitrogen plus hydrogen, where the nitrogen is blue, hydrogen is black, and you can see that at the start we have high concentrations of nitrogen and hydrogen, low concentrations of ammonia. And as the reaction proceeds, the concentration of the product increases, the concentration of the reactants decrease until you get to a point of equilibrium when the concentrations of all three are not changing. What if you now add to the system more of one of the reactants? So here we're going to add to the system a higher concentration of hydrogen. this will alter the equilibrium, and now we'll get further reaction until equilibrium is re-established. The same would happen if you at this point added some ammonia to this system. So you've added some product to the system, and so we would need, the reaction would spontaneously shift again until the system has reached equilibrium. So as you change a component of the system, you shift the equilibrium, and you'll get the reaction to move in one direction or the other depending on that change that you have made. What about changing temperature? So if you increase temperature, then you are adding heat to your system. And this will mean something different depending on whether the reaction is endothermic or exothermic in the forward direction. So let's consider an exothermic reaction. What will happen if we increase the temperature? Well, in an exothermic reaction, going from reactants to products, the change in enthalpy will be negative, and that means that the reaction produces heat. And the change going from products to reactants, where we will absorb heat, and the change in enthalpy will be positive. So, by increasing the temperature, we make the reaction take in heat, and this will shift the reaction towards the endothermic direction. If the reaction in the forward direction is exothermic, increasing the temperature shifts the equilibrium towards the reactants in the endothermic direction. So this changes the ratio of products and reactants. Changing temperature also changes the equilibrium constant. This table here shows you how. Okay, so you can see that if the reaction is endothermic in the forward direction, then a temperature increase will increase the equilibrium constant. So if it increases the equilibrium constant, what does that mean in terms of the relative amounts of products and reactants at equilibrium? It means that there'd be more products at equilibrium. And if the temperature decreases, then the equilibrium constant decreases. And for an exothermic reaction, then if you increase the temperature, the equilibrium constant will decrease, so you'll have less products compared to reactants, so it's shifting it towards the reactants. And if you decrease the temperature, the equilibrium constant will increase. Now we can show the link between temperature and equilibrium constant in an equation. And this equation is using these two equations that we have already seen. So that's the equation that the change in Gibbs free energy is equal to minus RT natural log K, and the change in Gibbs free energy is equal to the change in enthalpy minus temperature times the change in entropy. So these two equations, if you can combine them, you will get the Van 't Hoff equation that will link equilibrium constant to temperature. Now this is the Van 't Hoff equation, and so I've just magically combined those two equations to give this equation. You do not need to know how we've used those equations to derive this equation, but if you would like to know, because the maths could be a little bit complicated for that, then the last slide in this presentation will show you that. So this is the Van Hoff equation explained. We have two experiments, one at one temperature and one at the other, and at both of these temperatures the equilibrium constant has been calculated. So you have a T1 and a corresponding equilibrium constant K1, and a T2 and a corresponding equilibrium constant K2. And so the standard enthalpy change can be then calculated from a knowledge of equilibrium constant at two different temperatures. This summary slide initially looks complicated, but if you take time to look at it with the equations that are written at the above, you will see it helps to see what conditions lead to a negative delta G and therefore a spontaneous reaction. So looking at the top line, for a reaction that is exothermic, where delta S is positive, the reaction is favourable both in terms of entropy and enthalpy change. So delta G is negative under all conditions, and therefore K, the equilibrium constant, is greater than 1, and the reaction favours products. I suggest that you look through the other rows and see if you can make sense of each of the lines on this table. My final summary slide for this lecture, it provides an explanation of how G, the free energy, changes during an equilibrium reaction. Remember that K, ranging from anything from 0.001 through to 1000, will have reasonable amounts of both reactants and products, so will be an equilibrium reaction. But will the reactants be favoured or the products be favoured? First of all, let's look at this system here. In this system, K is greater than 1. Okay, and delta G for the overall reaction is negative. You can see that because the free energy of the reactants is higher than the free energy of the products. So the overall reaction has a negative delta G. So in a case where K is greater than 1 and where delta G is negative, you can see that the equilibrium point has it that products are favoured. There will be more products than reactants at this point. This is still an equilibrium reaction, but in this case K is less than 1, which of course means that reactants are now favoured. There are more reactants at equilibrium than there are products. And in this case, you can see that delta G for the overall reaction is positive, that the Gibbs energy for the reactants is lower than the Gibbs energy for the products. So the reaction will occur, but in the forward direction, but will have an equilibrium that has significantly less reactants in it than products. So in summary, this has been a whistle-stop tour of chemical equilibrium concepts, where I have thrown quite a few concepts at you that you may or may not have come across before. Quotient, and how the quotient links to the equilibrium constant, the relationship between delta G and the equilibrium constant K, and Le Chatelier's principle. And I've quickly introduced to you Van Hoff's equation. This last slide, most of you will be happy to ignore. It simply sets out the derivation that allows us to derive the Van Hoff equation from those two equations for Gibbs free energy, the change in Gibbs free energy at the top there, the one involving the equilibrium constant and the one involving enthalpy and entropy. So it's showing that process, and it's only for those who are interested in how I did that magic step from those two equations to the Van 't Hoff equation during the presentation. I'll leave you to take a look at it.